Action. Yes. So good afternoon, maybe good morning, everyone. So today my talk would be about global flows of foliated gravity matter systems. So this talk is based on our recent work, with my supervisor Frank and one former master student of our group, Goose, and in the title, the foliated gravity matter system means that we are going to consider gravity matter system on a foliated spacetime. Where we will make use of the ADM decomposition of the metric. And the global flows mean that we are going to consider the global structure of the RG flows, including the UV completion and also the infrared completion. So basically in this talk, we'll consider the global property of the RG flows of the graviton two-point functions for the gravity matter system. So here is the overview of my talk. First, I will give an introduction on our project, where we have the motivation for the research on the since we are working on a foliated space-time. Then next, I will introduce the ADM formalism on the other hand, we need to compute the RG flows of the graviton two-point functions. Then this computation usually requires the fluctuation approach. So next, I will give a very short review on the fluctuation approach. After we have all the background knowledge, I will give the setup of our gravity matter system on the based on this setup, I will also give our result on the fixed point structure on the flow diagrams of this gravity matter system. Finally, I will conclude the talk with a short summary on the outlook for the future research. Okay, so let's start with the introduction. So for most works in asymptotic safety program, they are carried out on a Euclidean spacetime. So to include the Lorentzian signature in asymptotic safety program, there are usually two ways to do that. The first way is that one could directly work with the Lorentzian signature or the Lorentzian spacetime. So for instance, for the spatial functional renormalization group approach, they just work with the Lorentzian spacetime. Or for the Wetterich equation adapted to the algebraic QFT approach, their method is background independent, so it doesn't matter if you choose a Lorentzian spacetime or Euclidean spacetime. So another way to to include the Lorentzian signature is that we could analytically continue the Euclidean computations to the Lorentzian ones by a Wick rotation. Usually, such a Wick rotation needs a preferred time direction to do the Wick rotation. So this time direction can be provided by the ADM decomposition. Therefore, the asymptotic safety program within ADM formalism can be regarded as a very important intermediate step towards the Lorentzian quantum gravity. So I think this is the main motivation why we consider the asymptotic safety within ADM formalism. In fact, the asymptotic safety program within ADM formalism has been investigated in several works. As a level of background approximation, it has been considered for both pure gravity case on the gravity matter system. Yeah, well, at the level of fluctuation approach, it was only done for the pure gravity case. Yeah, for example, in our previous work, yeah, we investigate the RG flow of graviton two-point functions. So, yeah, I want to give more details on this project since it's closely related to our current talk. So, first, the graviton two-point function could be given in this form. So here we have the Newton coupling, and we have the graviton mass, which is associated to the cosmological constant. Then in our previous work, we got the flow diagram for the Newton coupling on the graviton mass or the cosmological constant for the pure gravity case, which is given by this one. And we found that for the graviton two-point function, it is both UV and the infrared complete, yeah, indicated by this non-Gaussian phase point, yeah, which could be regarded as the UV completion under the infrared, under the Gaussian phase point, under the infrared phase point, which could be regarded as the infrared completion of the theory. Yeah, not only we found that for the RG trajectories bounded by the black lines, yeah, which connects those phase points. For those RG trajectories, they have the same infrared limit on the same infrared limit leads to zero mass. Yeah, since in this infrared phase point, all the trajectories are attracted to this infrared phase point, and for this infrared phase point, the cosmological constant is finite, so the renormalized mass would be zero for those RG trajectories. Then one possible extension of this research would be the inclusion of matter fields. Then after include the matter degree freedoms, one would then ask if the graviton two-point function would be still UV or infrared complete or not. Yeah, additionally, one would also want to know if the graviton two-point still have zero mass in the infrared or not. So to answer those two questions in this talk, we will consider the gravity matter system where we include N as scalar fields and NV abelian gauge fields. Those matter fields are minimally coupled to gravity. Yeah, within this setup, we will then work with the ADM formalism of the gravity and compute the flow of graviton two-point functions. Yeah, after we have the graviton two-point functions, we will then analyze the UV and the infrared completion of the theory. So that's the basic structure of this talk. So first, let's start with the ADM formalism. So the idea of ADM formalism could be given as the left panel. First, we could define a global time function on the manifold M. This global time function then introduces a foliation structure in the spacetime. Then the spacetime is foliated into a family of spatial hypersurfaces. After we have the foliation structure, then we can express the metric in terms of the geometric quantities, which are normal on the tangent to the spatial hypersurface. So here I give a simple example scale of a vector fields. For instance, if we have a vector field T mu, which is given by the red vector, the red vector, the green vector, then we can write it in terms of the components tangent to the hypersurface under the component normal to the hypersurface. Similarly, we can also do this decomposition for the metric. Then after we finish the decomposition, then the metric can be given in terms of the lapse function, which is a scalar field defined on the manifold on the shift vector, which is a vector tangent to the hypersurface, and also the spatial metric, which is the metric defined on the hypersurface. Then with the ADM decomposition, the metric degree of freedom is then encoded in those ADM in those ADM fields. Similarly, we can also do that for the action. For example, for the Einstein-Hilbert action, like we can also write it in terms of the extrinsic curvature on the internal curvature on the hypersurface. Here, R3 is the internal curvature, intrinsic curvature on the spatial slice on this curvature is constructed from the spatial metric sigma ij. And the extrinsic curvature could be given by the ADM fields, the lapse function, the shift vector, and also the spatial metric. So in this form, we fully read the Einstein-Hilbert action in terms of the ADM fields. So in this work, we'll adopt the linear split for the background method, which means for the spatial metric shift vector on the lapse function, we consider linear fluctuation of furthermore, for the spatial metric fluctuation, we'll employ the Yoke decomposition for that. Namely, we decompose the spatial metric fluctuation into the tensor modes, vector mode, and the scalar modes. Here, in particular, we are interested in the HIJ mode, which is the transverse traceless mode. We know that this mode is gauge invariant. In addition to that, this mode is also associated with 2 degrees of freedom of the graviton. This is the reason why we focus on the correlation function of these components in this talk, since it's really related to the physical degrees of freedom in the observation. Okay, since in this talk we need to compute the correlation functions, the RG flow of the correlation functions for these components. So usually such a computation for the correlation function needs a fluctuation approach. So I will briefly review the fluctuation approach. So let's start with a vertices function for the effective average action here. So usually the vertices function for the effective average action could be given in the following way. Here I only wrote down the the zero order term on the term quadratic in the gravitons, but in general there should be infinite series of terms there. So in this talk we are focusing on the term quadratic in the H fields. The coefficient in this term is related to the graviton to point correlation functions on the to evaluate the flow of this correlation function. We can take the functional derivative of both sides of the Wetterich equation. Like for the left-hand side of the Wetterich equation, after we take the second order functional derivative, we will have the the scale derivative of the graviton two-point function. For the right-hand side, for the right-hand side of the Wetterich equation, we will have the 3-point vortex on the 4-point vortex. Here, GK is just the renormalized propagator. So this means that, like, if we want to compute the flow of the graviton to point functions, we need the information about the 3 points on the 4-point vortices. In general, the couplings appearing in 3 on the 4-point functions are different from the ones in the 2-point functions. Like in this talk, to close the system on the simplified computation, we just identify the coupling from the 3 on the 4-point functions with the 1 from the 2-point functions. Okay, great. Then also we have the basic knowledge of ADM formalism on the fluctuation approach. I will introduce our setup for the gravity metal system. So in our work, we will introduce N as scalar fields on the N way abelian gauge fields minimally coupled to the gravity. That means for the gravity sector, the action would be given by the Einstein-Hilbert action in ADM formalism. Yeah, together with a harmonic gauge condition under the corresponding for the ghost and for the matter sector, we will have N as scalar fields, and we will have N way gauge fields together with their gauge fixing on the ghost term. So here in this talk, we just consider the abelian gauge fields. And in addition, like to simplify the computation, we will adopt the Euclidean on the flat background spacetime. Finally, to evaluate the RG flow, we need to specify the regulator. So in this talk, we'll implement the type 1 regularization. In this way, for the regulator function, we use the lithium type regulator function here. So with all setup, we could get the base function as following. So here, the first one is the base function for the Newton coupling, and the second one is the base function for the cosmological constant. And here is the anomalous dimension of the Newton coupling. So here B1 is just and also B2, they are just functions of the cosmological constant. And we can say that the anomalous dimension depends on the numbers of matter fields explicitly. So that means the numbers of the fields would affect the RG flow on the phase point structure in principle. Yeah, for the beta function of cosmological constant, like the function py on the p2 here are also functions of the cosmological constant. Yeah, for simplicity, we will not give the implicit. Yeah, we will not give the explicit form of them. So I'll just show the basic structure of those two beta functions. So yeah, here is one thing I want to stress here. So notice that in this talk, like we use the ADM formalism, yeah, which means we work on a foliated spacetime. So the Lorentz symmetry will be broken by our setups. So that means we will have two projection method to extract the beta function of the Newton coupling. So to see this explicitly, we can look at the two-point function of the graviton. Usually, the Newton coupling will appear in the external momentum part of the two-point function. For our case, since we work on a foliated spacetime which breaks the Lorentz symmetry, then in principle, the coupling in front of the spatial momentum part could be different from the coupling of from the coupling of the of the spatial momentum part. Then they will give slightly different RG flows for the Newton coupling. Yeah, in fact, like for the covariant case, those two factors should agree with each other. But for our foliated spacetime, they are usually slightly different, but they could give the similar qualitative structure for the bit function as well as the functions here. So yeah, I will not show the specific form of those functions for different projection in this talk. If we have time in the end of the talk, yeah, I will just give a picture of the plot of those functions. Yeah, after we have the beta function, then we can determine the phase point structure of the system. So first, we can look at the Gaussian phase point of the system. From the beta function, we can directly say that J equals 0, lambda equals 0 is a phase point of the system. Yeah, since the right-hand side just vanish. Yeah. Yeah, under this phase point, the existence of this point of this phase point is in fact independent of the number of ns on the n way. So this one will persist for all the gravity system with any numbers of matter fields. Yeah, next we will consider the non-Gaussian phase point of the system. So now to get the non-Gaussian phase point of the system, we need to solve the following differential equation. Then we can say that those two differential equations depend on the matter fields explicitly. So this makes the situation really complicated to analyze. So to show the result properly, first I will give the number of phase point as a function of the number of the fields. After we have the general picture of the number of the phase point, then we will look at the specific values of the phase point. Okay, great. Then first, let's consider the number of non-Gaussian phase points as a function of ns on the n way. So here I give the plot of the numbers of phase points for two different projection, P0 projection, and P vector projection. So for the orange zone, we have 3 phase point, non-Gaussian phase point there. For the red zone, we have 5 non-Gaussian phase point there, and for the blue regions, we only have 1 phase point there. So then by looking at those 2 plots, we could see that they could give similar structure or qualitatively same structure for the numbers of phase point. And also we can see that if we increase the number of vector fields or the scalar fields, the numbers of the phase point will just decrease, right? If we go along this direction, yeah, the number of phase points will just decrease. Yes. Yes. Then after we have this picture, then we can look at the phase point values of the system. So in this talk, I will just show the phase point values for 3 typical references points. First I will give the phase point value for this point, which is just a pure gravity case with 0 matter fields. Then I will increase the number of the fields to 4 scalar fields on the 1 vector field, and give the result for the phase point. And then I will also increase the number of the scalar fields of the vector fields to 10, and give the corresponding phase point structure. So first, let's look at the pure gravity case. For the pure gravity case, we can see that for this case, we have 0 scalar or matter fields, and we found that for both projections, we have 3 non-Gaussian phase points, and by looking at the critical exponents, we will see that only for the first phase point, their critical exponents are kind of independent of the projection. Well, for the other phase points, like the numbers of relevant direction will depend on the projection. So therefore, in this talk, we'll just regard the first phase point as the physical phase point, since their property, like the phase point position on the number of relevant directions are almost independent of the projection. Then next we'll go to the middle point where we have 4 scalar fields on the 1 vector field. For this case, we could find that for different projections, the numbers of the phase point would be different. However, but we could still find that for the first phase point, they persist for this system, and we also found that the property of their critical exponents are almost independent of the projection. That means like we still have 2 relevant directions for this point, and this result is independent of the projection. Well, for other phase point 2 and phase point 3, they still depend on the projection methods, so we will just regard them as the unphysical one. Then for the 2 new phase points in the p-vector projection, since this one only appears for this projection, we will regard them as an artifact of the projection. So in this talk, we we regard them as our physical one as the previous one. Just as the previous ones. Then finally, we'll go to the lots of phase point where we only have lots of point where we only have one phase point. For this case, we have 4 scalar fields and we have 10 vector fields. For this case, we see that only the second phase point, which depends on the projection method, will survive on the physical phase point, which is independent of the projection, will not be seen in this case. So this means that there should be a bound on the UV complete region, which is given by the green lines. For the regions below the green lines, they always possess a physical fixed point, which is independent of the projection, so it could serve as the UV combination. But for the regions above this bound, they only have the phase point, which depend on the projection, which is not physical. So for this case, we think they are not physically UV complete. So So in this way, we regard them as UV incomplete case. So also in this case, we can see that only the second fixed point. Maybe I should go. Only the second fixed point survive for the blue region. That means there might be a collision or annihilation of the fixed point, like the fixed point 1 and the fixed point 3, just meet with each other on the they just turn into the complete complete plan of the solution. So if we have time in the end, I will give more details about this. But first, I will go to the flow diagrams of the system. So now I give the flow diagrams for those 3 typical points here. So we can see for the pure gravity case, on the gravity gravity matter case with 4 scalar fields on the 1 vector field, they are UV complete. But for the case, above the bound, we don't have the UV fixed point on they are not UV complete, our G flow will go to the infinity, or they will end on the singularity of the beta function. One interesting thing that in addition to the in addition to the non-Gaussian phase point on the Gaussian phase point, we could identify infrared phase point for all those 3 cases. Where the infrared phase point is located at J is 0 and lambda is 1/2. In fact, this phase point persists for all the numbers of matter fields. The reason why we didn't find this phase point by solving the differential equation is that this phase point is located on the singularity of the beta function. If we look at the function here, we say that lambda is 1/2 is bound the singularity. So we cannot get this by solving the beta solving the beta function. So to confirm the existence of this phase point, we need to analyze the scaling properties of the RG trajectories in these regions. So in our work, we select several different RJ trajectories, and we found that for different trajectories, they just have the same scaling properties around that point. Since this property is independent of the trajectories we picked, since for different trajectories, like only the coefficient in front of them would be different, but the scaling property would be same. So we think this one should be a good limit of the RJ trajectories, and they could be regarded as a fixed point on the. One interesting thing that the existence of this infrared fixed point is in fact independent of the number of the matter fields. Yes, but the existence of this infrared phase point on the Gaussian phase point indicate that in fact the infrared completion of the theory could be independent of the UV completion, right? So this basically means that the infrared completion would may be a general structure or general feature of the theory, and this infrared completion maybe also could be found in other quantum gravity models, like the effective field theory approach to quantum gravity, where we don't have a UV completion, but then we could still have the infrared completion. So in addition, we could also check that for the infrared fixed point, which is independent of the number of matter fields, we always have a zero mass here. So we confirm that a zero renormalized mass is in fact independent of the UV completion of the theory as well. Okay, finally, let me conclude my talk on the outlook for the future research. So in this talk, we investigate the flow of graviton two-point functions for the gravity matter system with abelian gauge fields on the scalar fields. As our further result, we found that the UV completion of the graviton two-point function depends on the number of the matter fields, and we give the bounds on the matter fields for the UV complete quantum gravity. And secondly, we found the infrared completion of the theory is independent of the matter fields. And by analyzing the scaling property of the RJ trajectories around the infrared phase point, we can see that one could always get a zero renormalized graviton mass in the infrared, for any number of matter fields. And finally, if we combine those two conclusions together, we can see that the infrared completion is independent of the UV completion. So this means that the infrared completion may be a general feature of the quantum gravity, and this feature could also be seen in other approach, like the effective field theory approach to quantum gravity. Okay, then for the future work, one direct idea that one could also consider the influence of the fermions on the UV completion or LR completion of the theory. Also in this work, we only consider a flat background. So it might be interesting to consider a cosmological background. Then one could relate the result with the observation from cosmology or or other observations. Okay, this is my talk. Thank you for your attention.
Thanks a lot, Jian, for the nice talk.